All right. Hello, everybody. Thanks for joining us today. We're very excited for everyone to be here for this very important webinar. I'm John Wilson. I'm product manager here at USABlueBook, and I will be the moderator for today. We're thrilled to have two experts from the Hach company here with us today. Hach's been a leader in water analysis for over 85 years, developing instruments, chemistries, and software that help ensure water quality around the world is where it needs to be. USABlueBook has been Hach's premier partner for over 30 years and offers the most complete offering of instruments and chemistries available. Today's webinar, Mastering Disinfection and Monitoring and Control, What's Important, What's Confusing, and What to Do, will help you choose the right disinfection method that you should be using at your facility, why it matters, common missteps and how to avoid them, and when and how you should make process changes. I'd like to introduce our speakers for today. Vadim, the next slide. Vadim Malkov is Hach's principal application specialist and one of the leading voices in water analysis innovation. With decades of experience in the industry, he's played a key role in shaping Hach's solutions to better meet customer needs. Casey Hawkins is one of Hach's learning facilitators, working hands-on with customers in and out of the field. From calibrating instruments to teaching best practices, Casey brings practical insights to his sessions with customers based on their specific needs. As we go through the presentation, if you have questions, please add them to the Q&A. We've got a dedicated time at the end of the presentation to get through those. And with that, let's jump right in. Vadim.
Thank you, John. And let's begin with just overview of water disinfection methods, chemicals used in those processes, and the regulatory aspects, which is all important. So here we go first. The main water disinfectants and applications are enlisted here, presented in this table. And you can see here that chlorine gas or hypochlorite, the main well-known disinfectant, and then monochloramine is widely used in North America and some parts of the world. Chlorine dioxide is used also, but mainly for pre-oxidation phase of disinfection process, as well as ozone, hydrogen peroxide, peracetic acid, permanganate, and sometimes you have seen UV, which is a strong disinfectant, however, produces no residual, therefore can be used in advanced oxidation practices when it's needed because it creates no disinfection byproducts, etc. If you look through this table, you can see the positives and negative traits of these disinfectants, disinfection chemicals, and the cost of the disinfection is the big question, of course, and the driving force in the choosing of the disinfectant, as well as multiple other parameters as listed here in this slide. So we're going to be focusing on chlorine disinfection, because chlorine is a strong and an expensive disinfectant, and it has great history, very well known, researched. However, it has the high DBP formation potential. It sometimes provides safety and security concerns, especially when it's used as chlorine gas. And for the pre-oxidation or post-chlorination, it's probably the same set of positives and negatives as you can see. And besides drinking water disinfection, as it's listed here in this main body of the table, it is widely known and used for non-drinking water disinfection processes such as wastewater, industrial wastewater, in the CIP, clean in place processes, in food and beverage, etc. So let's move on to the regulatory aspect, which is most relevant to the drinking water production. And of course, we're going to be focusing on the North America here, because this is where we are. So for United States and North America, there are two major fundamental acts, regulatory acts that encompass all water production. And why Clean Water Act is important? Because it regulates the pollutants discharge and basically sets the background for drinking water production. And this Safe Drinking Water Act, it establishes the major standards for drinking water production in the United States and is set by the US EPA, and it's administered by the US EPA. And it sets nationally primary water regulations, drinking water regulations, and secondary drinking water regulations. The US EPA approves methods, not instrumentation, for drinking water quality monitoring. And those methods are split between ASTM, standard methods, and US EPA alternative methods. Now, when we are touching on the US EPA and states relationships from the regulatory standpoint, the US EPA sets major maximum and minimum requirements for chlorine in the however, this is at the point of entry, as you can see here in this table. And once it goes into the distribution system, I mean, the drinking water as a final finished product goes into the distribution system, this is where states, they have primacy. And the primacy, it's an interesting thing because primacy gives states a lot of leeway, and they can be used or cannot be used by the states in multiple regulatory aspects. Now, when it comes to the primacy, the states can approve or not approve some methods which already may be approved by the US EPA, and can use different methods to validate or verify the instrumentation which is used for regulatory reporting. And from that standpoint, we are coming down to the two major methods, Amperometric and Colorimetric methods, which are used to report chlorine residual in the US water systems, drinking water systems, particularly US and other North American countries such as Canada and Mexico. They regulate close to the US EPA requirements. Now, when we talk about those methods, they both can be sufficiently accurate. However, they are touching two different sides of the regulatory landscape: the standard methods or the alternative method, US EPA method 334.0. And here it's important and it's quite useful to touch base on what exactly is covered by those methods, standard and the alternative US EPA. See here in this slide the major aspects of the regulatory acceptance by those two methods. If we start with the standard method, which is standard method 4500 chlorine G, which is citing DPD colorimetric online or manual analysis. And this method is considered gold standard in chlorine residual determination. And it has a lot of positives. However, it locks the customers or the users, the end users of the equipment into one particular type of instrumentation, the colorimetric instrumentation. Now, the alternative method 334, US EPA method 334, provides basically, it levels the play field for different methods, and it allows the use of online Amperometric continuous online chlorine analyzers to be used for regulatory reporting. However, with the one major caveat, the IDC, which stands for the initial demonstration of capability. And based on the state primacy, the states can require method 334 or can accept method 4500, standard method 4500 CL for the method approval. And then instrumentation using this or that method may or may not have to be approved by the states based on the compliance with the US EPA method 334. The very important distinction, the methods or methods listed under standard methods, they already accepted and approved by US EPA. And as I said, US EPA does not approve instrumentation, it approves methods. And from that standpoint, the online Amperometric technology can be approved for regulatory reporting using the method 334. All right, it's confusing enough. So let's jump to the overview of available chlorine monitoring technologies, which is more technical, but less confusing, I hope. Look, chlorine testing can be done, as we have already mentioned, I already mentioned, by two different technologies, colorimetric or amperometric technologies. Now, if you look at those technologies, colorimetric is administered by two different techniques, the field or lab technique and online monitoring. And you can see representative instrumentation, which works with under one or another technique, either manual lab methodology technique or online instrumentation, which is automatic instrumentation. Now, if you look at the right-hand side of the slide, the amperometric technology is also represented by a laboratory and online technique, and those are representative instruments with one big caveat here. If the colorimetric technology is used across the board for field or lab, it's the same technology. For amperometric technology, you cannot say the same. Laboratory amperometric titration does not equal to online sensing technology. And now we're going to dive a little deeper into those technologies and talk about what are they? What are those technologies? So if you look here, colorimetric method or technology uses intensity of the color to determine chlorine concentration. And the deeper the color intensity, the higher the chlorine concentration. On the other hand, on the right-hand side, the amperometric technology uses electrical current or voltage, which is proportional to the chlorine concentration. And measuring this current or voltage provides the measurement of chlorine concentration. Now, the main differentiators, if you look here at this slide closely, the main differentiators are the influence of major water parameters, such as pH, flow, temperature, and calibration. On one hand, you see here, the colorimetric technology is independent of those parameters, and it has the established calibration curve. On the other hand, the amperometric technology uses no reagents. It's reagentless. It provides fast response to the analyte concentration changes. And those are the main technology differentiators. Let's focus on one particular aspect, the fast response to the analyte, which is a differentiator for amperometric technology. Let's look at this slide here. This slide demonstrates a hypothetical change in chlorine feed. For some reason, chlorine feed goes from 1 to 2 ppm. What is the response of continuous method or amperometric technology? It starts responding immediately. That's the biggest differentiator. Starts responding immediately. However, to quantify the change, normally two parameters are used, T90 or T95. It is time needed to reach either 90% of the response or 95% of the response accurately. So this time for all major technologies usually is about 100 seconds. But T90, T95 is about 100 seconds. Now the time to reach 100% is about 150 seconds if you use amperometric technology. And interestingly enough, that's the same time to reach, that 100% accuracy using batch analysis, colorimetric analysis. All right, now let's compare those two methods side by side. All right, you can see here, both methods are responding to the same hypothetical change in chlorine dosage or chlorine feed. You can see the immediate response at the very beginning of the continuous method, which is represented by the green line here. And at the end, you can see at 150 seconds, approximately, the batch analysis may respond with a full accuracy. Yes, that time may extend based on the sampling, and because it's a batch analysis, it grabs the sample, analyzes this, discharges this, and repeats the cycle. And you can see here, the difference is really, truly in, seconds, 10, 20, 30, maybe 100 seconds, maybe even 150 seconds if, the stars didn't really align well. However, the question arises immediately. What is more important, measurement accuracy or speed of response? And when we talk about speed of response, let's not forget about one important factor. When you use continuous analysis to drive your pumps, to control your process, use it via either PLC or PID loops, to avoid chattering, you need to average the results. You cannot immediately react because it's going to create a lot of unwanted consequences. And any control engineer will tell you, no, you cannot use the immediate response. You need really some kind of averaging here and there to avoid those consequences and the premature pump wear, etc. So that question remains. What is more important? But the answer may be lying here. You can have both. You can have both fast response provided by Amperometric technology and accuracy provided by the Colorimetric technology. It's how you use these methods and technologies together. All right, moving on to the other differentiator, independent of major parameters of the water, of the sample. Why does it matter? And what is the difference here? All right, this slide gives you major parts of the pH influence. And pH influence starts here when you dissolve chlorine in the water. Even when you dissolve hypochlorite in the water, it creates this equilibrium here. Why this equilibrium is important? It's important because we have HOCl as the main species here. Why is this main species here? Because Amperometric technology, if we're talking about comparison, responds only to these species. The sensors only seeing HOCl, hypochlorous acid, and they're not seeing OCl minus. On the other hand, colorimetric technology responds to both. Now, if we look closely at this chart here and the percentage of those species depending on the pH, you can see that 50% or 50-50 ratio is at about 7.5 pH value. You go to lower pH, you increase the HOCl concentration. You go to the right side, you increase your OCl minus portion. Why does it matter? Once again, if we're using Amperometric technology, it responds only to the HOCl. And if you go with a higher pH, the portion of HOCl goes down, lower, and with that goes down accuracy of the Amperometric technology. It's inevitable because there are much fewer species to really measure. Everything else needs to be deduced somehow. And if you think about normal drinking water applications, the pH is usually above 7, and sometimes it's above 8. How does it influence the response of those two technologies? Let's look at the just true experiment. These are experimental data, which I derived in the development of one of our main chlorine analyzers, the CL10. And you can see here, when pH changes from 7 to 8 through 7.5, the response of DPD analysis stays the same. It's 1 ppm. Amperometric response drops unless you have pH compensation. Now, what that means? That means that pH compensation is required for Amperometric sensors, no matter what technology is used or sub-method is used, whether it's a bare electrode system, whether it's a membrane covered system, but either external buffering, feeding a buffer solution into the water required, but that feeding external buffer means that it's not reagentless anymore. Internal buffering is used in Cl10, for example. It's highly potent electrolyte, which converts every OCl minus species into the HOCl inside the membrane cap, and therefore it provides the sensor with the right species to measure, increasing the accuracy. Or it can be mathematical compensation, as it is employed by the whole array of bare electrode amperometric sensors. Without pH meter or pH sensor, connected to it, it's just useless. And with a pH sensor, you need to think about that and ensure that pH calibration is correct. And all those things do matter. And all those things, they come from the application. So the application drives a lot of those nuances and very important parts of the choosing the right analyzer, right? So when we talk about applications, this is the very high level applications, overview and type as we came up with typing, and most importantly, regulatory expectations. So you can see here, there are some applications we can call static from the standpoint of changes in the sample conditions. And those applications are mainly regulatory reportable applications, such as point of entry, etc. Now, there are quasi-stable applications when the conditions may change, not necessarily fast, but they may change, such as like settled water or filtered water before clear well. Sometimes it changes fast enough when you feed the chlorine after the CFE into the clear well, and before the contact time is achieved and everything is settled in the clear well and the finished water, the concentration may still be dynamic. And then there are dynamic applications. There are constantly changing sample conditions due to the nature of the process and water sample. At a flash mixer, backwash loops, disinfection loops, CIP, you name it. So those applications are not usually reportable, but important for the process control. And from the process control standpoint, we already discussed that initial fast response may not necessarily be driving the right process control. All right, it's time to summarize the main online technologies currently available in the chlorine monitoring. And you can see here, once again, on the left side, colorimetric technology, right side, amperometric. And what are they? See, the colorimetric technology is accurate without calibration. Why is this? Because it's based on the physical law, which dictates proportionality between concentration of the analyte and intensity of the color. Now, colorimetric technology is independent of changes in sample pH, the chlorine concentration, temperature, flow pressure. On the other hand, what amperometric technology is, it is continuous. It provides fast response. It is reagentless, unless there are some reagents added for pH compensation. But most importantly, no reagents in the waste stream by definition. Now, amperometric technology is not accurate without calibration. Calibration is required. It is not independent of sample changes or sample quality change, such as pH, chlorine concentration itself, temperature, flow, pressure. And colorimetric technology, of course, it is not reagentless, not continuous. Now, a few words about amperometric method. I want you to be aware of some creative naming. Some manufacturers call their sensors polarographic, which is completely wrong and inappropriate. Polarographic method is based on the dripping mercury electrode. And of course, you cannot even imagine dripping mercury electrode in drinking water analysis, right? It belongs to a lab, to research, you name it. Please don't be fooled by the fancy name. It's the same Amperometric technology with all the same is nots. And main takeaways, reagentless technology does not mean it's maintenance-less technology. Calibration is required, may be required frequently, and other maintenance such as replacement of electrolyte, membrane cap, etc. But what's even more important, application matters a lot. So now let's talk about how we can use all this knowledge in choosing of the right online chlorine analyzer for you. So this is the selection guide, and this is outline of the thought process. So first, of course, you should look at the major performance specs. Then you need to consider each technology's differentiators as what we just discussed to determine which is preferred. You may need to research detailed specs to see what is most important for you in terms of accuracy, in terms of limit of detection, you name it. And finally, you need to consider your treatment process realities, which are the keys to application success, to make sure that the preferred instrument or the one you're looking at as the preferred is right for your application. Let's go step by step because it's a 4-step process, as you can see here. Step number 1, basic specs. You compare, most importantly, range. Sometimes, most frequently, Amperometric technology offers longer, higher, wider, broader range. Is it important for you? Is your concentration ever above 10 ppm? Maybe, maybe not. So that may be your first thing. Now you look at the range of pH. What is applicable? What is not applicable? And what is important for you? Is your pH in this range all the time? If yes, yeah, go for it. Go to the next step. And next step is basically repeating what specifications or what is preferred for your application, what differentiators are most preferred for your situation. Is it influence of sample pH? Is it calibration? Is it average routine maintenance? Is it reagents handling? Is it reagents in the discharge? Is multi-parameter measurement important for you? And you see here, each technology or each instrument based on that technology may give you the answer here, just when you look at the technology characteristics as we just walked through. Okay, step 3, what specifications are more suitable for your application? Is it limit of detection or accuracy? Is the accuracy of such and such better than accuracy of such and such? Is the accuracy depending on pH, like here for Amperometric? Then response time. Once again, same question. What is more important? Fast response or accuracy? Now, regulatory. What method is acceptable by your regulatory authority? Do you have to go through IDC or standard method 4500 or 40 CFR is acceptable? Automatic cleaning. Is it needed? Is it not needed? Etc. With this, you go to the last step, number 4, which defines the keys to application success. And the question is, can your utility meet these requirements? Can you do this at your place? Replacing reagents monthly, managing the waste stream. Is it required? Is it not? With the Amperometric technology, do you have uninterrupted sample flow? Do you have uninterrupted power? Is your sample pH stable within half a unit roughly? Is your concentration, chlorine concentration, stable roughly within plus or minus 20%? Those things are all important, and those are aspects of your application. Now, just to summarize the selection, Those are main questions to ask in every step. Does the measurement range good? Does the specified pH is good for you? What is the preferred for your situation and application? Accuracy or response? Speed of response specifically. What nuances of the specifications are most valuable for you in your application? Reagents handling and versus necessity of calibrate. What is more important? And with this, I'm gonna hand it over to Casey and the portion of instrumentation hands-on.
Great, guys. Hey, again, my name's Casey. If you can see behind me, I'm in one of our labs here at Hach in Loveland, Colorado. And I'm going to give us some instrumentation hands-on experience and talk about some tips to improve accuracy and troubleshoot common problems that might arise with some of your instruments. Next slide, please. These are the three instruments we'll be focusing on. We'll start with those colorimetric methods with our handheld DR300 and move on there. Thank you, Vadim. So yeah, first of all is our handheld DR300 pocket colorimeter. You guys are maybe familiar with this. Some of the pros for this instrument. It's very portable and hands-on. I have one with me now in my lab, and it literally is hands-on as long as your pockets are big enough, I suppose. And of course, it's very portable. If you guys purchase this instrument as well, we typically offer some sort of carrying case where you can store all of your sample cells, your reagents, as well as your instrument, so you can really do these tests in the field instead of waiting to bring everything back to your lab. So very good stuff there. And then we also currently offer 17 different options for this DR300. So we offer everything from ozone to chlorine, of course, as you see here, to monochloramines as well, ammonia. The list kind of goes on for another 17 options or so. But that's one of the cons as well. This is a single parameter instrument. If you are concerned with that little limitation there, relatively, this is an inexpensive instrument. So you could always purchase another type of DR300, or of course, we also offer our DR900, SL1000, DR3900 options that have multiple parameters. But yeah, go ahead, next slide. So a little bit of my hands on here. I'm going to keep right here as long as everyone can see me all right. If I was in a normal chlorine analysis class, I would typically ask the class if you know what color of light we're using for these kinds of analyses with chlorine. I don't expect anyone to have a DR300 with them, but if you do, go ahead and follow along. But you're going to go ahead and turn it on. It doesn't matter if you're in the low range or the high range there. And what I'm going to have you do, and what I'm going to do my best to get in this camera here, is I'm going to place my fingernail right here above that triangle, and I'm going to click this blank right here. And you should see.
I'm sorry to interrupt,
yeah,
Casey, but just for everybody on the call, if you do want to make Casey's video larger, you can click on the pop-out button, and that will open up that video screen in another window, and you can enlarge that so that you can see it much more easily.
That's great advice. Yeah, I am going to be doing quite a few things on my camera, so we want to highlight everything I'm doing. So yeah, again, so that's one quick way to find out that we're using a green light for this kind of test to measure our pink sample that we produce. Now is normally a time when I would talk about complementary colors. That green is the complementary color to pink, and that's why we're using a green LED. And you can imagine if you buy a different type of analyzer, that you're going to be using a slightly different LED, perhaps, with your different colorimeters there. What I want to talk about quickly next is that if you're ever wanting to verify the operation of your instrument, while these colorimeters don't require calibrations, they do require some verifications. You guys are probably also familiar, if you are familiar with our DR300, with our spec check standards. These come with a lot in expiration dates. These are secondary standards, so they're just, to verify the operation of our instruments. They'll have a certificate of analysis here. And the nice thing about these is that you come with one blank, and we give you 3 different gel standards here. You're going to run your blank and run each of those standards in your DR300. As long as the values you get on your DR300 match your certificate of analysis, you can feel reasonably confident that your DR300 is working as expected, that if you're getting any issues, that it's likely not going to be a result of your DR300. But that only verifies the operation of your instruments. If you really wanted to get a full spectrum confidence boost, I would recommend running a 1 milligram per liter standard. To run the standard, the big hurdle is that you would need to purchase some sort of chlorine standard, like the one I have here. And the hurdle here is that it's very concentrated standard, 62 milligrams per liter. Our range here is only to about 10 milligrams per liter. So you'll have to do some sort of dilution there to get your standard ready. But I believe that if you're ever having any issues with any of these test methods, either with chlorine or honestly any test, go ahead and run a standard. If you get a good number, that's close to your standard to be read on your DR300, that's going to be a good confidence boost that not only does your instrument work, but your reagents work as well, and your analytical techniques are also working as well. Sticking with the colorimetric analysis, imagine we take our DR300 and put it on the wall, and we hooked it up with some tubings for our reagents. We threw in a stir bar there, and we have a continuous sample stream that's not too dissimilar of our situation with our CL17SC. So the pros here is that it is a colorimetric method of analysis, so it matches our handheld and laboratory methods of analysis. We also offer now, if you're familiar with our legacy instruments, the big blue box from way back in the day. So we now offer an LED drive percent value. That's a real-time value. You're always going to be seeing that on your controller. So you can always see how clean your colorimeter is. You'll get warnings now if your colorimeter gets dirty to warn you to go ahead and clean that. But this is a value that you get to see all the time. Instead of finding that very obscure reference value in the old legacy instruments. We also offer an ultra low range instrument as well. This has an increased limit of detection all the way down to 8 parts per billion compared to the 30 parts per billion of our CL17SC. So if you are in a situation where you're constantly reading low and you really want that added confidence there, I would really suggest our ultra low range CL17SC. Of course, another pro is that this does not require calibrations, but we do require verifications of the instrument. Typically, those verifications are going to be done with a handheld or a laboratory instrument, and so that's a nice plus there. No more calibrations. Go ahead on to the next slide. So some of the cons might be that this does require some maintenance. Again, if you compare this to our legacy instruments, the maintenance is miles ahead improved compared to the legacy instrument, but we do have to replace that tubing kit about twice a year, as well as make sure that colorimeter cell stays clean. And that's something I normally recommend to do every time you do a reagent change, which is another sort of con. We do have reagents in this instrument, an indicator and a buffer. So of course that has a cost component. It also has means that there's some reagent in our waste stream that we have to account for. This is also doing a batch analysis. We're doing continuous 2.5-minute intervals of readings. And so we're not technically getting a continuous measurement reading, but really for all intents and purposes, this is just exactly what we need. Go ahead, next slide. So I'll talk about a few tips to what to do if you encounter any issues with your instruments. When in doubt, clean the colorimeter cell. At my experience back in the day as a field service technician, this would solve 9 out of 10 problems with my customers. Is just cleaning our colorimeter cell. And I'm about to walk us through that pretty quick here. If you ever have values that are off, that installation checklist, go ahead and run back through it again and make sure all of those parameters are still good. Make sure we still have that good water flow. Make sure that we're getting good flow of our reagents. We can test that. If we run a prime, we can disconnect that tubing that's coming out of that pinch block, and we can see in real time if that reagent is being supplied or not. The stir bar is an important part. It's also very easy to lose because it is magnetic. So make sure that thing is present and stirring. Make sure reagents are, of course, not expired or discolored. And as always, this is a big issue that would pop up a lot, back in my days on the road as well. If you're ever getting discrepancies between your handheld and your online analyzer, typically the problem with that was that we weren't taking our analysis or grab sample as close to the instrument's inlet as possible. If all else fails, you can always run a calibration using either kits that'll come with a chlorine ampule, or you can always do a comparison calibration using something like a DR300. I will say again, this is a last ditch effort. Typically, if you have to do a calibration, I find normally we have to undo the calibration in the future. I would again go through that checklist to make sure your instruments has good tubing and all of this other checklist values right here. So with that said, I'm now going to switch my camera over, and I want to really emphasize how quick some of this maintenance is done. This maintenance is done about twice a year, and what I want to show you is that to do this maintenance, I'm going to be using a kit that looks like this. It's going to have a part number and a serial number, and in my kits, what I have is a new tubing kit, and I have a stir bar. And again, you're going to be doing this about twice a year, every 6 months. And in order to do this, I hope you can see my SC4500 controller all right here. But again, if you haven't seen an SC4500 yet, this is what it looks like. Not too dissimilar from your phone or something. We have color and touch screens now. But I'm going to just press on the CL17, come all the way down to my device menu, and I'm going to go through the standard tasks of replacing tubing. So I'm going to go ahead and click OK here. And I want to make sure I'm in an output mode hold. Typically, whenever we're doing maintenance, we don't want any of these values to be sent out to our PLC or SCADAs. And while this is flushing my colorimeter, my cell, I'm going to make sure that my flow is turned off. And I'm going to, at this point, wait for my instruments to tell me when it's time to go ahead and do a tubing change. So I'm cheating a little bit. My reagents aren't connected just because, we're not typically running a real sample here. But as soon as I get a prompt and as soon as I get this green flashing light, I'm going to be told to replace my tubing. And first of all, I'm going to replace or remove my reagents here. Next, I'm going to disconnect my sample stream from my flow meter up here, another improvement over the old style. And what I'm going to do is remove this pinch plate and pull out my old tubing kits. Again, if you're coming from the legacy instruments, this probably seems much easier in comparison to the old style. To do our colorimeter cell cleaning, I'm going to kind of showcase that as well. Typically, I like to go ahead and remove our stir bar using something magnetic. I'm being creative and using a flathead screwdriver here. And here's when I would add in a few drops of my 5.25 normal sulfuric acid. That's going to be different compared to the sulfuric acid you're using with your legacy CL17. I would place a few drops into my colorimeter cell, and I would start then tackling each of these four corners and all four sides with my Q-tips. So Q-tips are still going to be around. I'm going to keep doing that with new Q-tips until I get a Q-tip that comes back that's no longer pink, purple, or black. And normally, in my experience, that can be anywhere from 3 to really 10 Q-tips. Who knows? It really depends how dirty, how long it's been. But when you're done with your cleaning, place back in your new stir bar. You're going to reattach your new, you're going to attach your new tubing kit here and place on your pinch block. No more over tightening of the pinch block that you might have seen in the legacy instruments. I'm going to connect my sample stream to that flow meter and reinstall my reagents. And finally, I'm going to place all of this back the way it was. Again, I'm cheating a little bit. And then I'm going to click OK. And now I'm going to be prompted that it's going to start priming. And that's going to be about a 180-second process. 3 minutes, I think, is really a lot quicker compared to, I think it was like 15 minutes with that old CL17. So that's as quick as it takes. That on the legacy instruments, that process would probably take me, 20 to 30 minutes, and here much quicker. So that's how you're going to be doing some of your maintenance with the CL17SC. And we can move on to talking about the CL10, the Amperometric. So I just showed you how to do some of the maintenance with the CL17SC. We're going to talk about the Amperometric now. The pros for this instrument is that it is reagentless and it has that continuous monitoring component. However, there is still going to be some maintenance required. We have a membrane cap and electrolyte component that are going to be needing to be replaced about every 3 to 6 months. We might lose some sensitivity in low and no chlorine environments. And we do require calibrations with this method, typically with something like a grab sample comparison. So some tips for your CL10, if it's not performing as expected, just go ahead and run through some of those maintenance items. And at the end of this, I'll briefly go through those maintenance items, but that's going to be including replacing the electrolytes and replacing the membrane cap and polishing the electrode tip. To do this maintenance, you can buy a little maintenance kit that comes with a new membrane cap, as well as a blue piece of paper that's kind of fancy paper that lets you do that polishing of your electrode tip. Like any other Amperometric device, please don't touch the membrane surface with bare hands or fingers. And we can have fouling that occurs of the membrane. This can be caused from anything from iron and manganese to sulfur-containing chemicals or surfactants and detergents. The nice thing is if you're worried about fouling of your membrane or at least the cap, go ahead and try to replace that cap and see if we can get some improved results, again, after some preventative maintenance. So some tips if you're having some issues with the readings or you're noticing some wide fluctuations. The general rule of thumb is, again, go ahead and try out that preventive maintenance checklist, especially focusing on the fact that your sensor tip might be oxidized. So it might be a good idea to go ahead and do to polish that up, and then go through that checklist of making sure that we're hitting all of these parameters, that we have that good consistent flow rate, good sample pressure, that our pH and sample conductivity are not out of range, and that we're in a chlorine concentration that's above 0.1. Again, if we're at 0.1, we probably want to look at maybe some other method of analysis. If you ever, this is typically something that happens after we do some maintenance. You might see a bunch of dashes that show up on your controller. This typically means, and most of the time, that your sensor just needs to be conditioned still. So I would just wait a little bit longer to see if these numbers start to catch up. Or you could be in a situation where, again, you're in a low chlorine situation. In this instance, we might want to try doing that chemical zero function. Or you could just be simply missing sample, or you have low flow rates, or there could be air bubbles in your electrolyte. So to just really quickly run through some of this maintenance stuff, I have my CL10 probe with me here, along with my maintenance kit, which is my electrolyte and membrane cap. And really, the only things I want to focus on is when you remove this cap, if you're changing out the electrolytes, go ahead and pour it all out and make sure you dry everything out to make sure old electrolyte has been removed. To polish my electrode tip, you're going to notice this blue piece of paper has a shiny side and a matte side. You're going to place that matte side face up on a hard surface. Now I'm just going to do several lines like I'm drawing with a pencil, and that should be good enough to polish my electrode tip. Whenever I'm installing my new electrolytes, I want to turn our attention to our membrane cap. This is something that I see missed all the time, and I really want to highlight it, that when you are replacing that electrolyte, I want us to see this, this little rubber piece, pull that down to expose a little hole that's on the side there. And we want that hole to be exposed so that whenever we add in our electrolytes, adding in our electrolyte with like minimal air bubbles added as possible. Whenever we get that filled up, and I place on my the body of my CL10, you're going to cause a little bit of a mess. So make sure to do this in a place where you don't mind to make a mess. You'll screw that in, and you'll see some electrolyte popping out of that hole. That's totally expected and should happen. When you're nice and tight back on there, go ahead and recover that hole again. Place this back into your sample stream, let it condition, and then, of course, always calibrate after you do any preventative maintenance. But with all of those tips, that should guide you guys and really, in my experience, fix, I would say, 90% of issues that pop up with these instruments. And with that said, that's my time, and thank you very much.
All right. Thank you, Casey. Thank you, Vadim. That was a very, very informative presentation from both of you. We do have questions lined up, and I will start tossing them out to the team. Does the form of chlorine inform the choice of your monitoring method? For example, chlorine gas versus sodium hypochlorite, or their likelihood to form disinfection byproducts?
Dissolving chlorine in any format in water, whether it's a hypochlorite, calcium hypochlorite, or sodium hypochlorite, or gas chlorine, it creates the equilibrium between HOCl, hypochlorous acid, and hypochlorite ion in the water. And that equilibrium, where it goes right or left, depends on the pH, as what we discussed in the presentation. But no, source of chlorine does not really create any difference for measurements. pH does. pH does, as we discussed.
All right. Next question. Thank you, Vadim. Next question is, making chlorine standards is very difficult because chlorine is so unstable. Do you have any recommendations or advice on making standards?
I would say one thing I've noticed in my experience doing this, I've traveled all across Pennsylvania for PRWA, running chlorine standards, and my biggest thing was the water source. Your DI water, not all DI water is created the same. So if I ever had any issues, sometimes I would notice that maybe one brand of DI water was slightly better than others. And so that's one thing you can tackle. You can also buy, instead of these large chlorine standard ampules, which are, pretty kind of intimidating, there are smaller ones with maybe a slightly less concentration than, 62 milligrams per liter. And so you might try different ways of, different types of dilutions. But typically, having ran this quite often, as long as you have the right tools, like a good pipette that you're, believe is accurately giving you, that 0.8 or however many mils you need, as long as you have the right pipette, a good volumetric flask, a good water source, and good unexpired reagents. Those are typically the big checklist items for making sure you have good standards for those dilutions.
Terrific.
Good
Thanks,
question.
Casey. Is the sampling interval adjustable on a CL17SC?
No, it is not adjustable. And I also took on that question while Casey was delivering his part. That was discussed many times. We as Hach, we want to be right. It's our logo here, right on my, left side of my shirt. And from that standpoint, we cannot risk compromising accuracy due to reagents aging, for example. And also the fixed 150 seconds interval provides very predictable monthly reagent replacement interval.
Okay. Thank you. Next question. Is there a way to test for concentration of potassium permanganate the same way that the DR300 does for chlorine?
That's a great question. And as a matter of fact, I personally developed method for permanganate using Cl17 and then expanded on Cl17SC. Total chlorine reagents, they respond 1-to-1 to the milligram per liter of permanganate as chlorine. So when you see a number, when you measure permanganate in the water and you see a number on the screen, that's the number of ppm or milligram per liter of permanganate in the solution in the water. We have 2 application notes published on Hach.com website. You can search for permanganate keywords resources. You'll find those application notes, and those notes detail how it's all done.
Good. Thank you, Vadim. Another question, if you're purchasing a CL10F, would you also want to purchase the pH option to compensate for slightly higher pH?
That's another great question, and it needs to be emphasized or re-emphasized that CLF10 has internal pH compensation inside the membrane cap in the electrolyte. So CLF10 is not designed to use any mathematical compensation from a pH sensor, which can be used and attached to the same gateway that block on the panel. With this being said, once again, pH sensor does not provide any external or any additional compensation for chlorine readings on CLF10 as well as CLT10. This is an option which is always good to have pH measured in your water along with chlorine concentration. It's always informative given all the equilibriums available in the water. And also that's addition of pH sensor to CL10 gives you a chance to save another port on controller, because all the signals go through the same port, and then with the one input available, you will have chlorine, pH, and temperature and the same one input to the controller. That's an added benefit.
Okay, thank you, Vadim. Next question. For the DR300 chlorine, under replacement items and accessories, potassium iodide and sodium arsenite solutions are listed. What are these solutions used for?
I know the potassium iodide, I mean, typically for that DR300, if you're doing a total chlorine test, you have a potassium iodide is just going to be added to your powder pillow. So you won't even really notice the difference. I mean, you'll get a powder pillow bucket that maybe kind of looks like my 1,000 powder pillow bucket here, but the powder pillows will basically look the same. It'll just have total versus free. I believe those are listed as items to buy, maybe just in case you're doing a slightly different method. But if you're using powder pillows, all you really need is that powder pillow and the right sample cell with your DR300, and that should be everything you need for either free or total chlorine tests.
Yes, I can only add a couple of words here to Casey's response. The arsenite is used as a chlorine scavenger. So in some situations, when you have interference from other compounds in the water, you can determine the value of that interference by killing the chlorine in the water and measuring that sample again. And the difference between the measurement without arsenite and with arsenite gives you the value of that interference.
Okay, thank you both. Next question. From a process control standpoint, is it feasible to choose only one method for adjusting the dosage of chlorine with a manually dosed system?
That's a good question, and we need probably to understand slightly what is a manually dosed system, because yes, of course, you can use any instrument, readings from that instrument to manually adjust chlorine feed, as long as you trust that reading. If you want to use the instrument to automatically adjust the dosage, that's a little different story, because then you need to use the flow input. They need to use some other inputs potentially to recalculate the dosage based on the flow and the readings of chlorine. And this is a closed loop control with either PID loop or with PLC. This is how it's normally organized for automatic control.
Okay, well, I think we're right about at time. I don't see any more questions. Again, thank you, Casey. Thank you, Vadim. And thank you to everyone who signed up and participated on this call with us. We will be getting a copy of the presentation emailed to everyone using the email address that you used to register. And thanks again for your time.